Hi, I'm an old guy and I do maths, and you don't often see a blank page when it comes to my work. But today we have a problem involving a coin and a die. And you'll have seen the problem set out in the header. The story is basically this. A coin and a die are thrown. The coin lands on with its head up, and we record the value, the face value on the die, which means 1, 2, 3, 4, 5, or 6. If, however, the tail is showing on the coin, we double that value. So 2, 4, 6, 8, 10, and 12. And our job is to sort out a probability distribution from which we can calculate an expected value or mean value for this event. Okay, so in order to sort this out in my head, I took a blank piece of paper and I did the following. So there's a head, there's a tail, and the probability is a half for each of those. And we have then 6 possible scores off this. So 1, 2, 3, 4, 5, 6. We can have a 1, a 2, a 3, a 4, a 5, or a 6, and the probability of each of these is 1/6. So, for instance, the probability of a head and then a 5 is 1/12. Okay, and it's 1/12 for each of these. Now, if we do the same here, we've got similar probabilities, but we've got different outcomes sometimes. So if we throw a 1, we double the score. If we throw a 2, we double the score. If we throw a 3, we double the score. 8, 10, and 12, like that. Okay, so that is how I sorted this out in my head. And each one of these has a probability of 1/12. Now, what is interesting when I consider the sample space of this distribution is I get the following. 1, 2, 2, 3, 4, 4, 5, 6, 6, 8, 10, and 12. That's all 12 possible outcomes, and you'll notice that there are double ups. So these are 1/12 each, and the same here and the same here. So when I come to set this out, as I would set out the problem, this is what I get. So let's have a look here. We have 1 coin, 1 die. Heads we get 1, 2, 3, 4, 5, 6. Tails we get 2, 4, 6, 8, 10, 12. I draw up my probability distribution. 1, 2, 2, 3, 4, 4, 5, 6, 6, 8, 10, 12, and each one of these is 1/12. But I can simplify this. That's the point. I can simplify this to 1, 2, 3, 4, 5, 6, 8, 10, and 12, and I can combine the probabilities here from 1/12 to 1/12 plus 1/12, which gives me 1/6. So my distribution isn't quite even looking, but that doesn't matter. This still adds to 1, which is what I would expect. Now, what is the expected value? That's actually fairly easy. It involves a calculator, but it is fairly easy. The really key thing is getting this distribution sorted out and the probabilities that come with it. So what is the mean or expected value? Well, it's each one of these times its probability. So 1 times 1/12, 2 times 1/6, plus 3 times 1/12, and so on, all the way up to 12 times 1/12. And when I work that out, that gives me 5.25. So the expected value from playing this game or whatever it is over a suitable number of times would be that my outcome would approach 5.25, which makes a degree of sense when you consider that there's an element of skewing towards larger numbers up here. Anyway, I hope that this helped with sorting out problems such as this, and I hope it made sense. If it did and you found it useful, please like and subscribe, and I'll see you next time. Bye.